let's get started. We're gonna get started. Okay. First thing to try out is Henri has posted an IP address that's going to be the Jupyter Hub where we will be doing this workshop. Please connect to that. We will give you your login information, but it should be your first name _ last name lowercase. And what's the password, Henri? Is it password?
So the password is PyArmNN123. I'll put that in the chat as well.
Perfect. Cool. So try, and if you're having issues, don't worry about it. We're going to talk for a few minutes, and then we'll help troubleshoot your Jupyter Hub issues. Sound good? Cool. Firstly, welcome to this Tech Talk. We'll be doing a PyArmNN workshop. I am Karl Fezer. This is Henri Woodcock. We are Arm AI Ecosystem Evangelists. If my screen works, there we go. Stay tuned for the next AI Virtual Tech Talks series, the next in line in this series. The next one is going to be hands-on. That's this one, hands-on with PyArmNN. The next one is going to be automate TinyML development and deployment with Keekso AutoML. That's going to be presented by Keekso. March 30th. The last two do not have registration links up, by the way, but if you're watching this on YouTube, then they do. So go check it out and register. But we just announced these, so if you're watching live like you are, then it's not up yet. But check it out soon. It should be up in a few days, by the end of the week at least, to register. March 30th is going to be Thermal Vision AI, creating TensorFlow models for thermal image classification. That's going to be with OpenMV. And then April 13th is, there's a zero in there. The first no-code voice AI platform for ARM Cortex-M based microcontrollers, and that's going to be presented by Pico Voice. So definitely check those out. All three have developer versions of their software, or it's meant for developers. So if you're doing this workshop, you're definitely going to be interested in those. These are your hosts. That's me, Karl, and then Henri is going to be working with you with the workshop. We are Arm AI Ecosystem Evangelists. We are going to do a quick overview of the ARM software stack again, just because that's what we'll be using today. If you have, just as an overview. So today we'll be working with ARMNN and specifically PyArmNN. So that's a Python wrapper for the ARMNN inference library. Basically, you have your hardware layers down at the bottom, ARM CPU, ARM GPU, or NPU drivers. The ARM compute library sits on top of that for CPU and GPU. And then ARMNN lets you interface with the compute library, just making it a little bit easier. The NPU will interface directly with ARMNN when they're physically available. For an in-depth talk on all of that, check out the last Tech Talk, the February 9th. That was for ARMNN and the compute library. I believe it's accelerating machine learning inference with the ARMNN 20.0 release. Sorry, 20.8 release. But that video is already up on YouTube, so if you want more detail, check that out. Okay, why use the ARMNN in ARM compute library? Versatile and portable, superior performance for ARM CPUs and GPUs, and then there's ARM-specific optimizations. Basically, it's all open source, so you don't have to worry about it. If you're developing on ARM and you're running inference, specifically if you're running like Android or Linux and bare metal, and you're running on an ARM architecture, these will help make it easier to get better performance, because that's effectively what those teams work on, and that's what these libraries are for. There are multiple framework integrations for Linux and Android. There's for TensorFlow Lite, PyTorch, and Tensor. It's a interpreter effectively. For TensorFlow Lite, the delegate has just been released. And that's going to be the easiest and the more performant way to go. Eventually, that will be the default way, but for now, that's like optional. If you're running an Android and the Android NNN API, that works with TensorFlow Lite and PyTorch Mobile. Debian packages were released in the last release in November with 20.8. I've tested it with Ubuntu Groovy on a Raspberry Pi. I would recommend the 8 GB of RAM version if you want to run Groovy. Some others have run it with the 64-bit version of Raspbian. Either way, you need a 64-bit operating system just to make sure like you get the performance benefits that you want. 32-bit's not supported for those packages. PyArmNN is basically just a wrapper for the ArmNN library. You can import it at PyArmNN as just like you would with any other Python library. And it's very easy to install with the Debian packages. You can see the installation guides are already updated on GitHub. We'll be updating all of our guides to update them with the Debian package install, and then we'll also be showing those steps at the beginning of the workshop. There's also a public model zoo. So these have been models that are optimized for ARM architecture. Right now, these are the 5 models that are up there. I believe everything is focused has an ARMNN version, except for Wave to Letter, I think, where it's just for our microcontrollers. These are useful links. We'll share these slides out later so you can get these. And with that, we will start the workshop.
So yeah, when you connect, you'll have just one file here called PyArmNN object detection. So you want to open that, and then you just want to open up the workshop notebook inside there. And then it should open up. So at the top here, I've just included a little brief instruction on how to install ARMNN and PyArmNN. However, I've also included a list of links which will help you install it yourself, and also a bit more information about it. So if you look here, there's just a few links: ARMNN, PyArmNN, and then there was a virtual tech talk 2 weeks ago on ARMNN, which just showed a few benchmarks. There's a link to the ARM model zoo there, where you can download more machine learning models. There's a link to the examples directory if you want to go through some more PyArmNN examples. There's an Arm ML examples repo, which covers both TensorFlow Lite and PyArmNN and ARMNN. And then there's guides to contributing to ARMNN and PyArmNN if you want to do that. So this notebook here is going to be doing object detection with PyArmNN, and it's based around one of the examples that you can find in the PyArmNN examples folder. And just as like sort of a way to start off, the PyArmNN repo examples folder is a really good place to start when you're trying to learn how to use PyArmNN. There's an object detection, an image classification, and a speech recognition example in there. So there's also a folder inside there which is called common, and that just gives you a lot of helper functions which sort of work in all 3 domains. So all 3 examples can use the same helper function. So it's just quite good to have a look at how it's all structured and how you can work on it yourself. So then after that, we'll just dive straight into the code, and you can run along with me on your notebook doing this. So we have a couple of dependencies just to mention here. There's NumPy or NumPy, and then there's also OpenCV. And if you've not used OpenCV, it's just a few helper functions really for working with video in Python. So you just want to run the first cell here, and you'll get this warning here. And this is because I installed PyArmNN with the apt repository up here. So all this means is the only backend we've got is a TensorFlow Lite parser, but there are a few others which you can install if you build it from source. Okay, so here's just the next few steps of how this notebook's going to go. So there's a few steps I've wrote down. First, we're going to import and pre-process an input video, and then we're going to create an output video, an output directory where we're going to start saving output videos. I just do this just so you know exactly where you're writing the output files to, so it's not like sort of overwriting another video, for example. And then we want to create something called a video writer, which is a function in OpenCV, which allows you to input a file name, and then you can start saving frames to that file. After that, we're all set up, and then we can import the model. So we're going to be using the TensorFlow Lite model here. We're going to be using MobileNet SSD, which is a object detection pre-trained model. You can find that one and many more at the model zoo, like I said earlier. Once that's done, we're then going to import something called a label mapping, which essentially just sort of takes the output from the model into something understandable. So it like will say which class the output is. And then finally, we're going to just do a few basic writing of functions to help you pre-process input videos and like sort of how you'd write an inference loop to do this yourself. Okay, so the next step is selecting an input video. So what I've got here is I've taken a video myself. So it's in the location inside videos, and it's called cut video. And then if you run this cell below, it's just a quick way for you to view the video. If it loads, I'll play a little bit of it, but it's okay. I'll leave that, but it's just a video taken from the office, and that's what we're going to be performing object detection on. So once you've done that, you want to run this next cell, and then this is now creating an output directory to save the video to. Again, it's not necessary, but it just sort of like helps you understand where everything is. So as you can see here, I've created a new path inside the same videos folder where the input video is, and I've just called it output. And this is just a bit of a hand in here in case I had already made the directory. So now we're going to check if the input video exists, and we're then going to read it with OpenCV into something called a video capture, and then we're going to check if the video opened correctly. So now, if we had an error there, we know there would be an issue with the video opening, so everything's working all right. So the next step is to get the frame count. Now, the reason you get the frame count is because the way you treat videos in Python is you're going to treat it as a set of different images, and they're your frames. So here, this is just creating like the number of frames you've got, which you're going to be looping through at some point to perform each individual object detection on. And then the next part is we're just going to create the output video name. So what I've done here is I've just called it object detection demo. And then this bit here is just giving it the same file format as the original video. So it was originally an MP4. So that's just going to make sure we have an output video called object detection demo.mp4, and it's going to be saved into the output video directory that we created earlier. Right, so this next step is just a few helper functions which sort of can help you clean up the code a little bit. They're not necessary, but essentially we're going to get the source encoding as an integer, and these are just quite simple methods which are in OpenCV, which you can call on a video capture. We're going to get the frame size, we're going to get the width and the height, and that's because we want the input and output video to be the same size. And then we're going to get frames per second for the same reason again. So then once you've run them, you will then create something called a video writer. And as you can see, the video writer wants the file name for the output video. It wants the encoding, it wants the frames per second and the frame size. So once you've done that, you've now got your input video ready, and you've got a location and a video writer, which is going to write an MP4 into a directory. The next part is to now work on the actual model. So we're going to be using the TensorFlow Lite parser. So this means you need a .tf-lite file, which is a very common format when you're working in with PyArmNN, ARMNN, but also when you're working with mobile networks like on TensorFlow Lite. So the way we're going to do this is I've got it located in the main directory, and it's just called detect.tflight. And then I'm also at the same time going to read in, well, I'm not going to read it in, but I'm going to just say where the location of the label mapping is, which is what I explained earlier. So if we just run this cell, it's just going to check if the files exist before we carry on, and we didn't get an error, so they do. Okay, so the next part is sort of setting up the ARMNN inference engine. So you have to select an ARMNN backend, and you can actually write your own custom backends. And essentially the backend just explains how the network graph is mapped to the hardware. So a few that are built in are the CPU graph, CPU accelerator, GPU accelerator, ethos N accelerator. So these are just backends that come pre-built in PyArmNN, and they're all ways to build your own backend. And then what we do from here is we create a list called backends or preferred backends. And this is just sort of so you can select your order of preference of which backend to use. So if you've got an ARM GPU compatible with PyArmNN, you might want to select that as your most preferred. And then if some operators aren't supported on that, you want to fall back to the CPU accelerator. Then if some operators aren't supported on that, you want to fall back to the CPU ref. So just because we haven't got a GPU here, I've selected the backends as this. And the way you put them in order in the list is the order of preference. And then this next cell here is just if you want to use the helper functions. We'll not be using the helper functions. However, it's just in case you wanted to, the model name is the SSD mobile net version 1. And there's a few helper functions that I explained earlier in the PyArmNN examples folder. Right, okay, so here's an example of, so I've commented this out, but this is some of the helper functions that we provide in the examples folder, and it would just allow you to skip a few of the next cells, but we're going to explain it step by step just so you sort of understand how it all works below the hood. So what we're going to do is we're going to create something called a network executor. So the way this works is you want to create a parser and a network file. So in PyArmNN, this is quite simply, so we're going to be using the TensorFlow parser. Again, if you've got one of the other file formats and you've got it installed to read those, you can use one of the other parsers as well. And then from there, you convert the network file into a network using a function here called create network from binary file. So if you just want to run that. And then you want to, so we created this list of preferred backends earlier. I did it like this just so you could like sort of see what I was explaining. However, what you need to do is you need to run that string through backend ID, because that is just sort of like a string that represents the backend, when really it's if you just put the string through here, that will select the actual backend. So now you've got a list of, I can show you that. So it's like a PyArmNN backend item there. And then here we're going to create an ARMNN runtime. And then finally, it's going to create an optimized network. So this is just done by running it through a function called optimize. So you've got your network, you've got your selected backend, you've got your runtime, and you've got your optimizer options. You can, from like most using, you will not need to change any options, so you'll just be fine to just leave them as such. And then finally, we're going to load the optimized network onto the runtime to get the net ID. And then from here, we're going to find the input binding info and the output binding info. And this is so we can pass data to the input tensors and we can take data from the output tensors. So this is just looping through the network to find the right information. So with all this in, we're now going to go through and sort of create the helper that I had explained before. So what we've got here is we've got a network ID, we've got a runtime, we've got an input binding information, and we've got output binding information. And then what we can do is we can create a class which just holds all this information for us. And then as you can see here, this has got an extra part in it called output tensors. And this is just a function which will take an output binding information and take it and put it into tensors, which we can then use. So with all that, we can create something called an executor. And then the final part to an executor is a way to run the inference. So the way to run the inference is you're going to pass in some input tensors and take the output tensors and then return the output. So here we've got something called execute network. It's got input tensors, which we're going to have as a list, output tensors, again, a list. We've got the runtime and the network ID. And then as you can see, these are the functions you use in PyArmNN to do this. So use something called enqueue workload, and then you take the workload tensors to an n-dimensional array. So if you want to run that. And then what I've done here is I've just called this function, I've added it as a method in a class called run. So execute.run equals execute network. So if you were to do this yourself, this is why we have this sort of like helper class here, which just sort of simplifies everything, because as you can see, that is something that you probably do quite a lot over different problems. So here we've just created a class to help us do that. Okay, so now one thing with object detection is you have to sort of like try and understand your model, and you'll get some model specific sort of like processing that needs to be done both to the input and the output. So models will expect like different size images to come through, or they'll work better with different sized images, or they'll work better if they've been standardized in a certain way. So here we've created a function here called SSD processing, and this is going to process the output. So the one thing that is a parameter that we can change really is the confidence threshold, and that's sort of, are we going to class it as an object above a certain threshold? And here we're taking like a sort of 60% confidence threshold, which is just the output values in the output vector. So what you sort of see is it's going to loop through. So what you get in an object detection output is you'll have like sort of a list of bounding boxes, and you'll try and classify each one of those bounding boxes, and you'll get a position, a classification, a confidence, and so on and so on. So what we're doing here is we're just looping through all these different detections and checking if the confidence is greater than the confidence threshold that we've set. And then if it is, we'll go through and we'll take the information about the bounding box out. And at the end, we're going to return a list of the bounding boxes. And then here's another helper function, which is just to get a resize factor. So the way that an SSD network works, without going too in depth, is you sort of want to have this factor which can allow you to resize the bounding boxes to fit onto the image. And then, so I've done this just in case you want to use a different network at some point, but essentially all object detection networks are probably going to have an output processing function and a resize factor. So I've just called them sort of like general names there, so you know you can just sort of use it like that. And the next step then is to import the labels. So I'm just going to quickly show you what a label file looks like just by reading in the first 5 lines here. And this, so as you can imagine, if you're getting an output between 0 and something for class label, then this is going to call on this label index, and you're going to get like, if you have like class 3, for example, 0, 1, 2, 3, and it's car. And then where you can sort of make this a little bit easier to use is we're going to add the so this is going to add the colors for the bounding boxes for each class. So for the unknown class here in RGB, this is going to be the color of the bounding box. Now the final step is the inference loop. So I've given a quick overview of how the inference works, but essentially we're going to be looping through and then at each, so we're going to loop through the frame count that we got earlier. We're going to take the video, we're going to read that frame, then we're going to run it through the network executor, then we're going to get the output from there, then we're going to convert that output into bounding boxes, then we're going to write the bounding boxes onto the output video frame, and then that's going to get saved in the video writer. So there's a couple more functions that we need just to do this. This one is just to resize with aspect ratio. And this is what I was talking about earlier about making sure your input is the same size as the input boundings in the PyArmNN network. So you need to have an image that matches the network's size of the tensors, like the image is expecting. So if you just run that cell, oh, I think I might, I don't know. So then there's also this pre-process. So these two sort of fall in shape with each other in case there's any other pre-processing, which here is to sort of like make sure it's in RGB and to make sure like it's a float 32. And then finally, sorry, I forgot to mention this bit, you're going to use a function called ANN.makeInput tensors, and that's just your input binding information and your resized frame from the video. Then that's going to return your input tensors. And then the draw bounding box function, I won't go into too much detail for this, but essentially it's just going to try and find the X and Y coordinates of the bounding box, and it's going to fit it to the frame based on the resize factor, which I mentioned earlier. And the labels here, sorry, is it's also got the color of the box that you want to use. And then finally, this is just a little function to add a progress bar. And then here we go. So this is the loop. So just before I run it, I'll show you, or I'll run it. Okay, so it's going to run through the frame count. It's going to check if the frame's present, and it's going to then pull the frame from the function called video.read. If the frame's not present, continue just means like go to the next frame. You can't open it. We're going to get the input tensors by using that pre-process function that I spoke about. Then we're going to get the output result by using the executor.run function. We're going to pass through the input tensors, the output tensors, the runtime, and the network ID. And then we're going to go and pull the detections from there by processing the output. And then finally, we're going to use the function called draw bounding boxes. And that's going to draw the bounding boxes onto that frame. Finally, video writer.write that frame, and we're going to update progress, and it's going to do that for all the steps. And then the last thing to do here is to call video.release and video writer.release, and that's just to finally like save the video into the right format. And then if we run, oh, so I forgot to mention this here actually. So as you can see, I've used the input video again as the final output. So you're going to want to change that. Sorry, I did realize that I made this mistake yesterday actually, but I forgot to change it. So let me just find out what I called the output video again in the writer. So it's just called output video file. So if you scroll down to the bottom and replace input video lock with output video file, that should open. And there you can see, so we've got bounding boxes there. It's not completely accurate as it was guessing cars or bicycles there. However, it's working at least. So the next step is something we just included to see if you want to quickly try and do this yourself. So what we've got here is we've got let me just comment this out. We've got a package called PyTube. So you want to import PyTube, and what you can do is you can go onto YouTube, I'd probably recommend a short video, but find a video, and then this function here, which we've got pytube.youtube, and you can put in a YouTube link, .streams.first, because it brings a list of versions of the video you can download, and then .download, and it will save a YouTube file into your directory on this server. And then you can try and go through the steps yourself and perform object detection on a video that you find. And if you have any cool results, let us know. Does anyone have any questions about that? Or are you all happy to just get started working on your own?
Yeah, thanks, Henry. There were a few questions while you were going, and I kind of answered them. Someone asked earlier if you can use it with Cortex-M, and I said, no, you can't do ARMNN with Cortex-M. I should have also added, for Cortex-M, use TensorFlow Lite Micro, which already pulls in ARM synthesis and an optimized library. And that's kind of a similar process, but the models you can run on microcontrollers are more limited, and there's a lot more optimization steps. And then there was another question from Lee, which, do you know if we have a TensorBoard installed on the server right now to visualize the models, both the unoptimized model and the post-optimized model?
I don't think we do have TensorBoard on here.
I don't think we do either. We'll do that. We'll have to do that for the next workshop, because that's a very good question and it's a nice way to see it.
Yeah, definitely.
Apparently Netron is installed with TensorFlow, but we haven't messed with it, so we can play with it.
Netron has got an online version as well if you want to take a look at the model online. Yeah, if you download the .tf-like file, you can upload it to the Netron website.
Here, I'll find that website. I didn't know that. Let's see. Cool. Yeah, here. I will paste this in chat, and if you want to look at these models, you can just download them from the Jupyter Hub and visualize them there. But for the next workshop, we'll add a little visualization step to it, because that is good.
Yeah, definitely. That is a good idea.
Anybody have any questions? Feel free to play around with this. Both of us will be online for the next 15 minutes, and we can leave the server up for another half an hour after that if you want to play with it. Feel free to download this notebook. The code is already online. It should be in the PyArmNN GitHub repo, is the application we're using. In the examples folder. Oh, there are questions. Cool. Oh, this was the question I was about to ask. Can you run this on a Raspberry Pi? Yes. So this one is meant to, basically, that's why we're doing the CPU only one. This code works on a Raspberry Pi. Let's see. Ken asks, I'm getting an error running the last cell. Value error, not enough values to unpack. Expected you got one. I'm trying to figure it out right now. The last cell being the...
I was just going to ask, is that the PyTube cell? That would be the last one on mine. So I might just in case the cell is a little bit different for some reason. Here's our...
Oh yeah, the PyTube cell. Ram, Sammy, you just said Cortex M4. Is that a question? If the question is, can you run it on a Cortex M4, I would say use TensorFlow Lite Micro. Can I run these on Nucleo boards? If it has a Cortex-A processor, then yes. I'm not super... I don't know all of the boards. And then the STM32 AI package. I'll have to look that up. I think they have their own acceleration library, which might be. Which uses, if you're using Cube AI, it's going to be it should be more optimized than just this one, or oh, that's the STM32 is the microcontroller stuff. So it uses SimSysNN built into it, I'm pretty sure. So again, that's a microcontroller. Jetson Nano, that is an NVIDIA. Like on the Jetson Nano, it does have a Cortex A on board, so I think you could use this library, but you're probably going to get slightly better performance with the NVIDIA GPU that is on the Jetson Nano, for depending on the application. Like it'll use more power, obviously, but if you're doing video encoding, that's probably going to be better off. What is the format of the optimized network? Yeah, the optimized network is also a TF-Lite file. And you can save it. It should save just as a different name. Let me look. It should say in the code. And you should see it in the directory, the save directory, once it's converted, because you're opening it. It should be called. Is the optimized network saved in the library, or is it just made and then run and then disposed? We might not be saving it. You should be able to export it though. But it would be a TensorFlow-Lite file. Arena, could the labels be out of order with respect to integer labels for the model in this example, like question marks being in place of trying? There's probably a simple bug, because it is like identifying objects well. So we haven't messed around with it much. So it could just be some errors. Oh, you got the error.
Yeah, I'm not. I've got to apologize. I'm not sure what's happened with this PyTube function. I got it working yesterday, and now it's it's saying that it expects another value.
Weird.
Right, let me just. I'm gonna have a quick Google.
Yeah. Okay, cool. Yeah. Yeah, Irina says the label file is integer, one integer off. Thanks. That's probably, that makes sense.
Right, okay.
Be a...
so yeah.
Yeah, so everyone you can tweak the label files by an int. And I think the label files that should be available on the model zoo should be correct. This one's incorrect. Thanks, Arena. Fix the workshop.
Okay, so I'm not really sure what the error is, because I've done it exactly the same as their example on the website.
Yeah, I'm not a PyTube expert. I've just like used it for this, for exactly this, and I've never had it run into errors.
No, yeah, sorry about
any
that.
Other questions? Yeah, we'll try to figure it out or play around, and there's other ways to get videos. Is everybody having that PyTube error? If not, any other questions on ARMNN or Cortex A stuff or Cortex M or SimSysNN or machine learning models on ARM? Open questions? Let me find my PyTube.
I'm not sure.
Yeah. Any other questions from anyone? Oh, here we go. What does the parser do to the input that is linked to the model framework on an XTF flight? Is it formatting or is it something more? Ooh, that is a good question. Like a question to the ArmNN team, what exactly is the parser doing? I could guess, but I'd probably be wrong. It's not changing the model. So I know that the way the delegate works, which is the kind of the new way moving forward. So the TF flight delegate, basically I believe the parser is more of an interpreter. So basically it'll take the model and we have like one-to-one relationships with some of the layers. The issue is that we don't have one-to-one relations like that kind of interpretability with all of the layers, which is why like with the parser you have to add, if you're running a custom like layer or something that's not supported by the parser, you've got to fix that yourself. So the delegate does the interpreter, but then it has a fallback to TensorFlow Lite if just in case like you're running a model and we're for some reason ArmNN doesn't support that specific layer, you don't have to worry about it if you're using the delegate and it'll fall back to TensorFlow Lite. It just got released and it's not super well documented, but that's why we're moving to that way because it's as efficient and way easier because you don't have to worry about unsupported layers or models. I think that's the way it does it in my head. I could be wrong. I'll check with the ArmNN team. I think they answered that question last week in the YouTube video as well. Basically explain the difference between the parser and the delegate. That's what I remember. Hopefully that helps answer. Basically, moving forward, use the delegate. For now, this is using the parser, this example. There should be an example using the delegate coming out soon. Developer.arm. Yeah, check out, if you have more questions on ArmNN, I should say, watch the video from last week because they answer more. But I will also check and I'll post the answer on the YouTube for this once it's posted. So we'll get back to you virtually. You know, Henry, was that an okay answer from what you understand?
I think so, yeah. I think
That's the way I understand it in terms of like, it's basically, it is kind of changing, it's basically changing the model so that it's a way that ArmNN can understand it. And if there's a layer that's not supported and ArmNN doesn't know, then it just fails, which is mostly how like inference engines works. Like you have, like someone has to manually write all the supporting functions. Where that's why the delegate's so nice because you've already got if you've got TensorFlow installed, you can just fall back to TensorFlow Lite and let it handle the parts that the ArmNN doesn't understand. Any other questions? If not, we can probably wrap up and we'll leave this server running for another half an hour and let you play with it, even though the PyTube pip is broken somehow. There's still other ways to play around with it. There's also the other, if you go to the examples at the top of the Jupyter Hub, there's the GitHub link for all the other ArmNN examples. Those should work on this installation. I haven't tested them all, but we just tested this one. But since ArmNN is already installed, you should be able to download those, run those examples on this little server. And all of that, if you have a Raspberry Pi, you can do it too. Raspberry Pi 3 works. Raspberry Pi 4 is better, especially if you want to do the install from the packages method. And you also do need a 64-bit operating system for your Raspberry Pi. So either Raspbian or Ubuntu Groovy. Okay. I will put up their.
Yeah, just in case anyone missed it, if you're downloading this notebook, remember to increase the class index by 1 to get the right class names from the dictionary.
Yeah.
But
yeah.
yeah,
The
we were
GitHub
one
version
up.
is correct. So if you download it from GitHub, you can do it. And for this one, just fix the index. That was a good call. I saw that, I think, once, and I was like, oh, that might just be an index thing. But I just think it's funny that handbags are ties. Same. Anyway, thanks again, everyone, for joining. If there aren't any questions, we'll wrap it up. Tweet us at ARM Software Dev. Check out the ARM YouTube channel. Check out the ARM Software Developers YouTube channel. Thank you, Ken. Sign up for our next AI virtual talk, and then don't forget to fill out the survey to get a chance of winning an Arduino Nano 33 BLE, which is a great way to get started with TensorFlow Lite Micro, because it's got a little accelerometer, it's got a little microphone, and it even has, like, I think it's technically called a camera, but it's more like a very sensitive light, and can do colors. So there's a lot of good examples on the TensorFlow Lite Micro repo for that. Thank you very much.
Thank you, everyone.